To understand why giving an AI a massive context window doesn't solve coding problems, we must look at what happens after multiple iterations. Every single time an autonomous agent processes a prompt, it wakes up in a vacuum. It treats each new inference cycle as an entirely fresh universe, completely devoid of prior architectural intent. Because of this amnesia, it solves immediate local problems by spinning up new files and weaving ad hoc dependencies together. Over time, the project accumulates an overlapping tangle of redundant logic. Expanding the model's memory does not fix this. Being able to perfectly recall past errors is entirely different from applying a strict set of architectural rules to the present moment. The solution requires stepping outside the language model entirely to establish a constraint field. This is a singular, stable doctrine of architectural laws that persists independently, surviving every session reset. We enforce this field using the Builder Constraint Contract, or BCC. It operates as a mathematically rigorous, binding set of instructions that governs exactly how the agent is permitted to behave. First, the BCC dictates strict spatial geometry. It physically restricts the exact folders and paths where the AI is authorized to write its code. Second, it dictates topological routing. All state mutations must flow through explicit hierarchical paths, stopping the agent from creating hidden side channels. Finally, it dictates persistent memory separation. The agent's operational history and onboarding notes are physically isolated from the actual runtime software artifact. Raw context is not docked-in. Without a binding legal framework dictating the structure, autonomous coding inevitably collapses under its own weight. The first tier of the constraint field establishes absolute topological boundaries. We enforce strict write domain isolation directly at the file system level. This diagram maps the outer perimeter, the project workspace root. The agent observes this space, but cannot modify anything outside the active project. Adjacent, we define the tooling sidecar, an isolated subfolder holding tools outside the core artifact. We place an absolute barrier between these spaces. Sidecar tools cannot become a runtime dependency for the vendorable codebase. Inside, the reference reservoir functions as a curated library, holding inert legacy patterns for the agent. When the AI reuses a pattern, the bounded extraction rule forbids verbatim copying. Instead, specific logic hunks must be carefully pulled across the barrier and cleanly rehomed into the target structure. During this process, the agent is required to scrub those extracted hunks of any environmental coupling or hidden dependencies tied to their original location. By enforcing these rigid physical perimeters, we guarantee the final codebase remains structurally isolated and completely decoupled from the tools used to build it. With the external perimeter secured, we move to the internal geometry of the project root. Here, we apply the single domain rule. Under this rule, every generated artifact, whether it's a source file, a dataset, or an active module, must own exactly one coherent area of responsibility. There is an absolute prohibition against blending distinct functions. An agent cannot mix UI rendering, business logic, and data storage within the same component. To connect these isolated pieces, we utilize a manager layer. However, these managers are strictly bounded, permitted to coordinate no more than 2 or 3 adjacent domains at once. And crucially, managers are forbidden from absorbing actual implementation logic. They can route and sequence commands, but the execution must remain inside the underlying domains. For high-level coordination, the orchestrator rule restricts overarching nodes to either a defined UI layer or a core layer. This prevents orchestrators from sprawling across the entire project as unbounded global authorities. If any logic component exhibits ambiguous or dual ownership, it inherently violates the contract. The agent is required to halt and immediately refactor the component into smaller, properly owned units. Imposing strict single-domain ownership denies the AI the option to create convenient catch-all files. This directly neutralizes the mechanism that causes architectural rot. Even with isolated components, autonomous agents will freely connect logic modules together until they form an unreadable web of dependencies. We counter this with the runtime control graph. This diagram illustrates a mandated state topology spine, starting from a singular composition root. Unlike an unconstrained environment, the contract explicitly bans sideways cross-calls. Peer-to-peer manager connections are blocked. All state mutations must traverse strictly vertically, flowing down through approved routing spines. Information moves using message envelopes. Splitting open this glowing pulse reveals a strict data vehicle containing the sender, target, action, and payload. At the base, the SQLite logger acts as an append-only ledger, visibly journaling every successful message dispatch for traceability. To keep routing efficient, the envelope lightness rule forces massive data payloads off spine into a separate storage bucket. Within this structure, individual runtime nodes may maintain only an extremely narrow, isolated layer of local operational state. The true project data and global state remain anchored at the top, strictly owned by the composition root's dominant authority. Centralizing the control graph guarantees that every logic mutation the agent generates remains completely hierarchical, completely traceable, and strictly governed. Before any of this work is saved, we implement the truth layer separation rule. This explicitly forbids the AI from blending its own operational context with the production code. The data consumed by the actual runtime software must remain physically and mathematically distinct from the AI's internal builder memory. We isolate the agent's memory into the builder memory journal. This append-only continuity ledger is stored strictly within the project's designated documentation root. All work is executed in a tranche. A tranche is a highly bounded slice of work, defined by explicit non-goals designed to prevent scope creep. An autonomous agent is required to declare its current tranche and establish these boundaries before it initiates any substantial logic implementation. Once the work is done, it executes the Park Phase Closure Protocol. This outlines the exact validation and provenance checks required to successfully seal a completed tranche. If the agent fails to write identical closure records across designated continuity surfaces, the tranche remains unparked, and the code commit is deemed entirely invalid. By deliberately isolating the builder's memory, the AI's operational history safely survives session resets without ever contaminating the final software package. Because the agent is forbidden from linking to external workspace files or its own sidecar tools, the resulting software core is a self-contained package. By stripping away accidental environmental coupling, the codebase remains a vendorable artifact that can be moved or handed off without requiring its original build environment. The BCC replaces the model's tendency to generate ad hoc solutions with a requirement for strict adherence to the project's predefined geometry. It forces the agent to operate as a systems engineer, where every file and route must satisfy a mathematically defined constraint. To protect this structure, we enforce the final behavioral constraint, the pushback rule. The agent is legally bound by the contract to reject any prompt from a human user that violates established domain boundaries or introduces architectural fragility. Instead of blindly executing a dangerous instruction, the AI must actively warn the user of the structural consequences and propose a compliant alternative. Simply adding length to a large language model's context window only increases the radius of its potential architectural damage. Instead, true code-based survival requires an active, governing legal framework that constantly overrides the model's baseline predictive behavior. Scaling autonomous development depends entirely on the precision of the constraints. Reliability is a function of how effectively the agent's boundaries are architected.